Hello, everyone, and welcome to this special interview edition of the Daily Space. I have with me a wonderful guest who I will introduce in just a moment. Now, the reason that we're bringing you so many scientists this week is because we here at CosmoQuest want to keep the science flowing. Right now, with all the crazy things going on in our world, a whole lot of conference presentations are getting canceled. And I, for one, am bitter because I wanted to see all the science. So we're going to reach out to people and bring them here so that me, you, and everyone else can enjoy the science. Now, I would like to introduce you to Alex Morgan, who has the best email username ever, Morgana. And he's going to talk to us today about Mars runoff. How are you doing, Alex?
I'm doing very well, or as well as can be in these circumstances.
Well, yeah, the world went sideways on us, but do you at least have science that you can get done from home, I hope?
I do. I had some field work canceled, but mostly it's all remote sensing work, and I can do that from my computer.
That is excellent. I'm feeling completely spoiled because I work from home anyways. But um we'll make it work. And right now, I'd love to introduce your talk. And for those of you out there watching, I am being mean and controlling all the slides. So this lovely human is going to have to tell us when to advance the slides. Um, but I'm going to switch things over. Your slides are now on screen, Alex, and tell us all about runoff on Mars.
Great. So thanks for joining. And if you just want to go to the second slide, the one after the title.
We're there.
So we often think of Mars as this very different place from Earth, but in many ways it's quite similar morphologically. And so if you look at these two pictures, one would be forgiven for not knowing which of these was the Martian surface and which was the Earth's surface. The image at, if you go to the next slide, please. The image at the top is a Gale crater taken by the Curiosity rover, and the image at the bottom is a photo I took in the Atacama Desert in Chile. Next slide, please. So Mars today is dry and it's cold. It's not the kind of place you'd want to spend a nice day. If you go to the next slide. And this is because it's so dry and cold, liquid water is not stable at the surface. The conditions never reached the triple point of water. But it wasn't always this way. Next slide, please. If we go to look at the Mars geologic timescale, um, next slide. Uh, there's a general transition from Mars when it was in its early history, when it had a magnetic field, there was volcanism, and there appears to be surface runoff from rainfall. And then there was a transition to the next slide, please, as it got drier. But in that earlier period, we see that there were valley networks, there were lakes. We see those in the image at the top right, where you see a valley flowing into a crater and then outflowing the other side, showing that the crater was once filled with water. And possibly even oceans. This is still a bit controversial, but the possibility that there were oceans in that image at the bottom is topography. And so the blue areas are low, which color is the same as water, somewhat misleadingly, I guess. Next slide, please. And so there's lots of evidence for widespread fluvial, which essentially means river carved modification early in Mars's history. But the prevailing climate remains controversial. It's unclear whether it was warm and wet, whether it was cold and icy, whether it was something in between. And the discharge, that's the amount of water that flowed through these channels, these rivers, is a hard constraint on the prevailing hydrology and thus the climate at the time that they formed. Next slide, please. And if you could start the animation there. And so besides characterizing the former climate, paleo discharge is really important for characterizing landing sites. So on the left is an image, this is a color stretched image showing the mineralogy of the Jezero Delta, which is the landing site of the Perseverance rover, which will be launched later this year, hopefully still. And on the right is a landform evolution model. And these landform evolution models, they simulate the surface, they simulate how the surface of Mars or any planet changes as it's affected by other boundary conditions. And so discharge is used as an input for these models. Next slide, please. And there's been a lot of work characterizing past flow conditions on Mars. And this comes from a really rich history of characterizing past flow conditions on Earth. Next slide. And on Earth, we really care about this. Next slide. Because we have gauge data going back about 100 years. This is done through a network that the United States Geological Survey has maintained since the early 20th century. And one can imagine how you might measure the discharge. If you're on a gauge stream, you measure the depth of the channel, you know the width, and you can get out how much water is going through it. This is a lot more difficult if you're dealing with a ephemeral, so that's a stream that flows part of the year, or just a stream that hasn't flown for millions or billions of years, as the case on Mars. Next slide, please. So how does one determine the discharge in a river? So the discharge by a mass balance is going to be equal to the width times the depth times the velocity. Next slide. But say you're on a ephemeral river, like this one. This is a photo from Death Valley. Next slide. And so this is an alluvial river. And next slide. And alluvial rivers adjust their geometry to their boundary conditions. So the river's cross-section, so the width and depth, changes as a function of bank strength, a lot of times that's vegetation, the viscosity of the flow, the sediment supply, and et cetera. And so there's a single discharge that's somewhat representative called the quote unquote channel forming discharge. That represents the stable channel geometry. There's this quote that comes from Copeland, who's with the Army Corps of Engineers, that the channel forming discharge is a theoretical discharge that, if maintained indefinitely, would produce the same channel geometry as the long-term hydrograph. Next slide, please. And we often approximate the channel forming discharge as the bankful discharge. And this is the discharge that's flowing when the river is is flowing right at its banks. So in this cross section here from the USGS, it's cut off, but where it says natural levee on the lower left, the L is cut off, so it says natural levee. But the levees form at the edges of the river, and bankful is when you have levee to levee flow. And this is observed to occur on a 1 to 2.5 year recurrence timescale. And in this quote by this classic paper by Dune and Leopold, the bankful stage corresponds to the discharge that's where your channel maintenance is at its most effective. That is the discharge, which is moving sediment, moving or removing bars, forming or changing ends and meanders, and generally doing work, results in the average morphologic characteristics. I feel there's a couple words missing from that quote, but in any case, next slide, please. So how do we measure the bankful discharge? Next slide. And so especially we're interested in how to measure it if we're not on the ground and we're looking down from remote sensing images. This could be either satellite data, or the image on the right is a aerial image from a airplane. Next slide, please. There are two general approaches. One of these is the physically based threshold approach, and the other is the empirically derived correlative approach. And I'll go through what these are. And I apologize to Pamela, because there's a lot of different slides here to advance. So next slide, the threshold method. So imagine a hypothetical river on this diagram on the left. And next slide. And so the river we know that the river must be able to transport the sediment that's on the channel bed. And imagine you were to go out to a river and pick up the sediment at the bottom. These could be rounded cobbles, they could be boulders, they could be sand. We know that the river is transporting that sediment. Next slide, please. And so we know that the discharge from the earlier slide is equal to the velocity times the depth times the channel width. And we can measure a few of those out in the field. Next slide, please. Velocity, we can estimate using the Weisbach equation. And for this, we need the gravity, we need depth, we need slope, and we need this friction factor, which basically represents how much friction there is that the water is interacting with at the bottom of the channel. Next slide, please. And F can be approximated using the channel depth and the grain size. There's a lot of numbers in there, but the key bits are the variables. Next slide, please. So we can measure channel width and slope from remote sensing data. So in this image, we can just measure width using a ruler and Google Earth. And then slope we can use if we have good topography. So that can come from, on Mars, we have the laser altimeter, the MOLA instrument. We also can do what's called photogrammetry, which is where you use two images that are slightly offset from each other, and then you can get topography from it much in the same way that you can perceive depth by binocular vision. So next slide, please. So from that, everything, the variables in green are what we're able to measure. And the ones in blue are the ones that we calculate or not sure of. And next slide, please. And in red are the variables that are not measurable from remote sensing data. And so we need to find a way to figure these out if we're going to calculate the amount of discharge flowing on Mars. Next slide, please. So if we were in the field, you could measure, that's a typo where it says D84, it should say H.
Oh,
That's my fault. We could measure the depth easily if you were in the field. You would measure just what it is from bank to bank. Next slide, please. But this isn't easily measurable from remote sensing observations. A lot of the topography is not good enough resolution to resolve this. So we're going to make some assumptions. One is that bed load transport, so that's the transport of the sediment at the channel bed, is going to occur at bankful conditions. So when the channel is flowing at its banks. Then we're going to assume that the boundary shear stress, so this is the stress of the water flowing over the channel bed, at bank full is approximately equal to the critical boundary shear stress. The critical meaning the shear stress that must be attained for sediment to start transporting. And we're also going to assume that this critical shear stress is slope dependent. And there's a lot of experimental and modeling work that supports all these assumptions. So next slide, please. And so this is the same slide as before, but just with the equations in there. The only new things we're adding are this variable A, which just represents the sorting of the sediment. So the D84, that was from an earlier slide, that just means the 84th percentile grain size. The D50 is the median grain size. And then P is essentially a measurement of the density of the sediment. Next slide, please. So this is everything we have. So we still don't know the grain size, though. And that's kind of a, next slide, please. And that's kind of a big problem with the threshold method, because there's no way to really get a good sense of grain size on Mars. The HiRISE instrument has a best resolution of about 25 centimeters per pixel. But most of the time, if you're looking at a channel, in a river channel, the sediment's going to be a lot smaller than a quarter meter in size. So in the next slide, so the correlative method, what this is folks have gone out to the field and measured the bankful discharge and then measured the channel width and come up with a correlation between width and discharge. And it actually follows a really close correlation. This oversimplifies a lot of controls, to name a few: the sediment supply, the bank strength, the flow viscosity, et cetera. But it works pretty well. And so if you go to the next slide, just question, how well do these work one versus the other? Because before we apply one of these methods to Mars, let's test it out. So you go to the next slide. So we're going to test it on about 110 alluvial stream reaches on Earth, where we know what the bankful discharge is, and we can measure the width from satellite images the same way we would on Mars. If you go to the next slide. So there's a lot going on here, so don't really worry about the details. The point is, everything, the blue and green, is the ranges of potential discharges, because we don't know what the grain size is. And if you take anything from this, it's basically the discharge could be anything. We really don't know what is very well, just because we don't know what that input grain size is. So we have to approximate. Here we're approximating something between 2 centimeters, so about gravel, up to about the HiRISE resolution. So the threshold method is going to have some problems if we're doing on Mars, because we could have a huge range of potential discharges that we're measuring. If you go to the next slide, the correlative method. So there's still a lot of scatter on here, but it's a lot more condensed. And this seems to be a lot closer. I should have said this on the previous slide, but the x-axis is the reported Q, so the reported discharge. So it was measured in the field, and the y-axis is what we estimate using the same methods we would use on Mars. So we're going to use the correlative method for Mars because it seems to work better for channels on Earth. And if we go to the next slide, the next thing we have to do is actually find the channel reaches on Mars. So there's a number of valley networks on Mars. These were one of the things documented in the early Mariner missions, and have been one of the main pieces of evidence for that there was fluvial activity on the Martian surface. And next slide. And the first step is to find the interior channel, because the width of the valleys isn't necessarily the width of the channel that was flowing through them. And the way to picture this is, if you go to the next slide, imagine we're at the Grand Canyon. the valley is not the same thing as the channel. The next slide. The valley is going to be much larger. So if we were measuring the discharge going down the Colorado River, if we were using the valley width, we'd have some problems. It wouldn't work that well. So next slide, please. And then the slide after that. And so the red arrows indicate the valleys, not the channels. And so this is, so the first thing we have to do is find the channel. So if we go to the next slide, on here you can see that we have, so on these you could see the valley is the wider in the red, and the channel is incised in that in the blue. And these channels are not very common on Mars. Part of this, these valley networks were active 3 billion years ago or more. And so a lot of these channels have been eroded since then. But many of them are still there. And so if you go to the next slide, there have been a few cases looking at these channels, a few other papers looking at these channels and trying to extract discharge out of them. A lot of these are either individual case studies, so they found one channel and did the calculations, as in this top one. Some of these were older studies, so this work by Ross Irwin, this was back in 2005, and they just didn't have as good resolution data. They did not have the CTX data, and they didn't have high-rise. Or there's this recent work by Edwin Kite and colleagues, but they were mainly looking at younger channels. Just what I meant by that on the next slide. We're interested in this earlier period of Martian history. Kite was looking at this later period, which is extremely interesting and very exciting because it potentially expands the period that there was significant water on the Martian surface. But it's not what we're interested in for this work. So if you go to the next slide, see on this map, this is an ongoing project where it's a global survey for valley network interior channels. The stars are ones that we've identified. Purple and green are earlier work, and in black are the mapped valley networks, just for reference. On the next slide, here are 6 examples of these interior channels. The ones in red outline channels, and the ones in light blue outline inverted channels. Well, what's an inverted channel? If we go to the next slide, inverted channels, we see these on Earth, and what can happen is a channel can become, the grains inside of a channel are often coarser than the overbank sediments. So anybody who's been down to a river can see this. In the channel, you might have gravels where overbank it's mud, and you subject that to a lot of wind erosion. The wind is going to strip away the overbank sediments, and you're left with the channel in inverted relief. So it was formerly a valley, or not valley, but it was formerly a trough, is now a ridge. And we can calculate, similar to the correlative equation approach shown earlier, the discharge can correlate with the wavelength of the meanders. So it's a couple more slides. So if we go to the next slide, so getting from discharge to runoff. So if we can calculate the discharge, what we really want to know is the runoff. So that's the amount of water that was coming from the watershed area, which is outlined in red on this theoretical channel here. Next slide, please. And so this graph here, this is sort of our work in progress. This is ongoing. And this is just comparing the results we have with what Irwin and Kite had. And they're similar, but we're trying to, there's still a pretty big range of scatter. So if you go to the next slide, the key bit is that the runoff rates that we're calculating are on the order of centimeters per day, which is too great that what could be realistically be supplied by ground highs. Really, these values are similar to on Earth precipitation fed runoff and floods. And next slide. And just sort of conclusions from ongoing work is indicated there's precipitation that carve these valley networks and form these interior channels. We're continuing to search for interior channels across Mars. With the final goal, we'd really like to look at spatial trends. So if some areas had more runoff forming them and other areas had less, and what that might mean for input for climate models. And that's all.
And that's a lot. This is really cool work. And I love how you're combining, okay, so we're stuck on this planet. We're interested in that planet. Okay, so we can take the same kinds of images on both worlds. Now let's go out and test our hypothesis on Mars by doing field studies here on Earth. And sometimes recognizing that the same physics that's working here is working everywhere. And in your case, the same geophysics is working everywhere. It allows some really cool work to be done. Now, questions came in left and right while you were talking. So I'm going to scroll up to the top, and Folks, I'm probably gonna not ask all of them, so some of them hold till tomorrow, and I'll take care of them. Um, so scrolling. Oh, I scrolled way too far. Um, Scroll your fail. Um, so Henny's Ververb asks the classic question: are there any air phenomena that could cause river-like features?
You mean so? Probably not. So a lot of these, you can have features like yardangs and things similar to that that might have similar inverted channels kinds of things. But for these, probably actually now that I say that, it's quite possible. So for even some of these interior channels, uh, Mars has been subjected to billions of years of active wind reworking. And so for some of these, it is quite possible that these could be later carved by the wind. In some cases, if I don't know if the slides are still up, but if you go back to
I'll
slide,
switch him back. Hold on.
okay, up to slide 50.
Okay, let me. There we go. So slide 50 is on the screen.
Okay, so there's 6 examples here of interior channels. The one at the bottom center, uh, where you can see on the right, kind of on outside of the red box, it's almost kind of a dendritic network spreading out, and that you wouldn't really get from the wind in the same way.
Okay,
Of
and dendritic is the fingery pattern that you
Yeah, yeah.
get.
And so the flow here, it's collecting and then incising down into the smaller channel. But this is part of the thing on Mars where it's difficult in geologics. We're dealing with these features that have been there for a long period of time. And there's this term equifinality, which is the idea that different processes can end up having features that look the same morphologically.
That
And
that's a word I've never heard before. Can you say
yep,
it again?
equifinality.
Equifinality.
Yep.
That's
Um, for these, I mean, there's a number of other signatures we can look for to determine that these are fluvially formed. One are things like meander bends,
uh-huh.
where we would see the different bends of each meander. Another is different kinds of bed forms. Another is if in high rise, if we were able to see boulders that would have been transported by the flow, big rocks to be in high rise, the wind would never be able to move those from place to place. That's also pretty diagnostic.
Now DPI 209 asks an interesting question. Mars is a lot smaller than Earth, which means that when you go from a high altitude to a low altitude, that is a much larger percentage of the total planet size than you'd get here on Earth. And wow, are there mountains on Mars?
Mhm.
Are there any places where you have to actually add in the differences in gravity into your modeling as you go from high altitude to low?
Not so much that, not there isn't much. None of these valley networks in here are on the higher altitude mountains. It still is. I mean, even though Mars has these really high, a lot of topography, even relative to the Earth, it's still pretty small relative to Mars's massive diameter. It's still less than a percent. And most of these, there are some valleys that have been found on. I'm going to mess it up. It's either Alba Mons or Arcia Mons,
Which are
uh,
volcanoes.
which are large volcanoes, not as big as Olympus Mons, but
Right.
still very mighty compared to anything on
Not
Earth.
every volcano
Yeah,
can be Olympus
very
Mons.
true. Yeah, if only. Um, and so there are some features that have been identified as fluvial channels on near the summit, not quite the summit, but on the slopes of that. Um, but we're not really looking at those. These are more at lower elevations than
Okay.
that amount.
Now, you made it really clear how grain size can matter in terms of what's left behind, but it's less clear exactly how grain size matters when it comes to calculating flow through. Can you go into that in a little bit more detail?
Yeah, sorry, can you repeat the question?
I why does grain size matter in calculating throughput?
Mm. So the part of it is the big unknown for trying to understand a channel, especially for using the threshold approach on Earth or on Mars, is we don't know what the depth of the channel was.
Right.
But we know that if you go out to a river on Earth somewhere and you see grains in the channel in the river, at some point the river is moving those grains. unless it's possible they fell in from a hill slope and now they just have to be eroded down to a certain size before they can be
So
transported.
they're a diagnostic, not a cause.
Yeah, let me catch myself there. They can be a bit of a cause in that the grain size are going to affect the roughness at the bottom of the channel.
Yeah.
So you can imagine a river going down a perfectly smooth surface, say a pipe, is going to move faster than if it's on a really rough bed.
Right.
And in the same way, a river going over sand, all things else being the same, might move faster than something moving over a lot of grains because the friction is going to uh, slow down the flow.
Okay. So grain size is actually something that it's kind of evil that you can't go out and measure because it would allow you to both get a sense of, well, just how long did that flow do that thing that created those grains and how did it affect the flow of the material?
And this was something the Curiosity rover near its landing site observed rounded gravels in the conglomerate
Yeah.
rock.
Yeah.
This was Becky Williams had a paper on that. And then there was some later work where they were using the size of the grains and the rounding of the grains as a diagnostic for how far they had been transported. And so, yeah, it can be used in that sort of way too.
Now, we're all amused and excited by the fact that whether it launches in 2020 or 2022, the next NASA rover on Mars is probably going to have a helicopter on board.
Yeah.
Do you know if they're planning for that little drone to be able to go out and visit some of these riverbeds?
So my understanding is it's mostly a proof of concept
Right.
type mission. And I think it has 3 flights that it's planning on doing,
Just
which
three.
is very exciting in its own. But I would hope for that. I mean, just from there's this we can see a lot in high rise. I mean, high rise is incredible, but there's a gap between what you can see in high rise and what you can see in the rover. And the rover can only move so fast and
Yeah.
cover so much ground. So having something in between to go out and scout locations and be able to measure small channels that might not be easily resolvable in high rise would be
Now
very
let's
cool.
let's put some scale on this. High rise is very similar to lunar reconnaissance orbiter data, which is what I work with. They're sister
Mhm.
spacecraft. Um, I know with LRO we're getting 20 to 30 centimeters in our best images, and on average half a meter per pixel.
Mhm.
High rise isn't quite that good, but it's similar, I believe.
It's similar. I mean, up to 25 centimeters per
Okay.
pixel, which I'll talk to geologists who only work on the Earth, and on the Earth, the best you can get for commercial data is about 40 to 50 centimeters per
Right.
pixel.
Right.
The intelligence agencies have better, but that's not
They put
available to the rest of us.
restrictions on everyone
Yeah, yeah.
else. But Mars, the rovers that we put there tend to have things like video cameras and even microscopes.
Yep.
So there you're counting grains of sand and sometimes
Hmm.
taking them apart and seeing what's inside of them.
Hmm.
Um, so that is a very different sense of scale. So you can get good from space, but you can get great from on the surface.
Yeah. But one could imagine something in between where on the meter scale or something where something in between of what the high rise is able to get and what the curiosity or
Now,
perseverance rover can get.
the great question on many of our minds is when did the water flow? And we know that it was order of billions of years ago. But does your research allow you to get a sense of how quickly, how slowly Mars dried out in the past?
Uh, Not so much with this. It seems to have been relatively rapid
Okay.
in some
Define
cases.
rapid. Geology's.
Yeah, I need to be careful if I phrase this. It seems it was over a very short period of time that the valley networks were active.
Yeah.
But what's become more intriguing is really over the past 10 years, there's been a number of fluvial features that were active well after the Noachians, during the Hesperian, even the Amazonian. And one could imagine if these were active, these other features were active, there might have been reactivation of valley networks as well. Um,
So I
so
lost the first half of that sentence because Zoom took a moment.
Oh, yeah.
Um, I caught that there was reactivation, but I didn't catch what was before that. And the word reactivation is extremely exciting. So,
Mhm.
can you say the first half of your sentence
Uh,
again, please?
yeah, so it was sometime around the end of the Noachian to the very earliest Hesperian, so that's about 3.7 billion years ago, when the valley networks were really at their peak. Most of the valley
Right.
network insertion happened. In the last 10 years, there's been a lot of work looking at alluvial fans, some deltas, these smaller valleys that were all active well into the Hesperian, even the Amazonian.
Oh,
Um,
wow.
so up until billion years ago, which long time ago, but still relatively late in Martian history. And so it's not really exactly clear, I think, how the valley networks might have been reactivated later in their history.
That's
Um,
cool. Now, I could keep you here all day, but we're about to have another scientist join us.
mhm.
But before I say thank you, I want to ask, what is the next big question you're most excited to be able to get to explore?
So one thing related to this in particular is how really getting to the question you asked, so how long it took to form the valley networks. And so kind of as a two-part thing, one, just what's the volume of the valley networks, how much sediment had to be moved, and then applying sediment transport models to see how long did it take for that to happen. Um, I think that's something that would provide some insights into what the prevailing climate was like at the time.
That I look forward to seeing that research. Now, if people wanted to read more about what you're doing, where is the best place that they should go looking?
So I have a Twitter handle that I try to be more active, which is at Geology on Mars. I'm surprised I was able to score that
That is an
handle, but
excellent one, and I'll make
um,
sure that that lands in our notes for this episode.
great. Yeah, then we have a fair bit on the Air and Space blog. Um, the folks from the Center for Earth and Planetary Studies, where I'm at, regularly post things there about ongoing work that we're doing.
That sounds awesome. And I hope that we're able to have you on as your research advances to keep following this story because, well, water on Mars is one of the most fascinating stories our solar system has to ever so slowly reveal to us.
Absolutely.
Well, thank you so much, Alex, and go off and have a scientific day. And
I will.
I'm glad you're someplace warm. I'm watching you there in your t-shirt while I'm sitting here freezing.
Yeah.
Um, so thank you and good luck.
Great. Thank
Bye
you.
bye, Alex.
Have a good day.
All right, everyone. So we are expecting our next guest any moment. I'm going to throw up the standby screen for just a minute while I swap around the names and titles. And I will be right back in just a moment. So here is the awkward transition is awkward.